Welcome back. Today we are going to look at stability criteria in thermodynamics. Now, in our earlier classes, what essentially we have done is that we have shown that a system maximizes its entropy as it goes to an equilibrium state, right? Now alternatively the statement can be recast or said in terms of the energy, that it minimizes internal energy, its internal energy as it goes to an equilibrium state. Now in mechanics we have learned about different kinds of equilibrium: a stable equilibrium, and unstable equilibrium. There is yet one more kind of equilibrium which we are not going to talk about in this lecture or in this course, but which is very relevant particularly for people who study classes system. That is essentially what is called the metastable equilibrium. But we are not going to talk about this. Our idea now concerns is the following: that given a system in its equilibrium state, in its stable equilibrium state, what does this stability criteria mean? So we will first look at the entropy. So we will look at entropy first. And as stated before, the equilibrium state maximizes my entropy, or the entropy of the system, right? So now consider that we have two systems, and for each of these systems there are it's described by variables x1 and x2, right? So then let's bring these two systems together so that the combined system can be described by the variable x1 plus x2, correct? In which case, if you were to write down the entropy, particularly the maximization of the entropy, then this would mean that S of x1 plus x2 must be greater than equal to S of x1 plus S of x2. So following is the experiment that you are doing, that you have two systems, and each of these systems, let's say the first system is described by a set of variables x1, the second system is described by a set of variables which are x2. Now let's bring these two systems together so that these two systems come into a joint equilibrium. Now in this process of coming to a joint equilibrium, it maximizes its entropy, and once you have that, then you write down this maximization relation like this, because your joint system is now described by the set of variables x1 plus x2, and therefore the entropy is going to be of the joint system is going to be a function of x1 plus x2, and the maximization would mean that the entropy in the final state is more than the entropy that you started off with, right? Think about it now that you have a single system, and suppose you can partition these two systems. The extensive variables, which are these x1 and x2, so these are your extensive variables that you have that can describe the systems, and this extensive, you can partition this single system into two subsystems which are denoted as x1 and x2, such that the above inequality is violated. Then what is going to happen? Then the system as a whole would be unstable. If this inequality was not violated, then the system would be in a stable equilibrium. But if this inequality is violated, then the system is in an unstable equilibrium, and it would immediately separate out into two separate systems, right? It will break into the smaller systems, each with variables x1 and x2. So this is exactly the idea behind the stability criteria. Now a function with such a property, with this particular property that we have written down, is what is called a, let us write down completely, a function which obeys the above inequality is called a concave function. But what does this concave function mean exactly? For this, what we want to write down, if we want to understand the geometrical property of this inequality, let us write down x1 as lambda times y1 and x2 as 1 minus lambda times y2, right? Where we put the condition that lambda is greater than equal to 0, less than equal to 1. Then it follows that s of lambda y1 plus 1 minus lambda y2 is greater than equal to s of lambda y1 plus s of lambda. x2 is 1 minus y2, so we will write it down as 1 minus lambda y2. And now we use the homogeneity property of the entropy to write down s of lambda y1 1 minus s of lambda y2 is greater than equal to lambda s of y1 plus s 1 minus lambda s of y2. So we have come down from this above inequality, we have rewritten this inequality in a particularly different form. Now to understand this equation further, we will consider a system where we have a single extensive variable, let's say x1, or sorry, let's say x would be the general. So we consider a system with a single extensive variable, say x. Now if you want to do the mapping, which we with the earlier lectures that we had, recall that our fundamental relation always had the form for a hydrostatic system s of u, v and n. Similarly, u was as a function of s, v and n. So we can consider a system when we have a single extensive variable where we do not allow any fluctuations in v and n, so they are held fixed, or it could be we do not allow any fluctuations in u and n and v being held fixed. Something like this way we are thinking along this line. Then this follows that if I have the function, more generally for such a function I would have f of lambda plus x1 1 minus lambda x2 is greater than lambda of fx1 plus 1 minus lambda fx2. So the idea is that I want to have a geometric interpretation of this inequality. And to make our life simple, we consider essentially a system with a single extensive variable x, and that essentially is like looking at a function of one variable. So therefore I have just written down this inequality in terms of a function of one variable. Now if I want to look at the plot, so here is x1 and here is x2, and I have something like this. Now clearly if I look at this value, then this value is f of x1 and this value is f of x2. The quantity lambda x1 plus 1 minus lambda x2 is any value which is in between x1 and x2. Therefore, the left hand side that you see here corresponds to the value of the function at an intermediate point lying between x1 and x2, right? So this is, it can be anywhere over here. So if you choose lambda is equal to half, if you choose lambda is equal to half, then you see that you have come up with x1 plus x2 divided by 2. So it corresponds to an intermediate point. This particular an intermediate point between x1 and x2, and therefore f of lambda x1 plus 1 minus lambda x2 is essentially the value of f, the function. There is something wrong with the surface at the intermediate point. Look at the right hand side. The right hand side says that essentially what I have as lambda f of x1 plus 1 minus lambda f of x2. That is essentially belongs to the line joined by fx1 and fx2. So this inequality, if you carefully look at this inequality, this effectively means that the chord is below the curve. There is nothing essential about, I mean, there is extreme, this idea is extremely simple. If I just look at the inequality, the left hand side essentially corresponds to any value f of x lambda x1 plus 1 minus lambda x2, and this is the value of the function, and that must be above the chord. So essentially this inequality tells you that it's a concave function is essentially one where the chord is always below the curve. However, the problem with this thing is this inequality essentially does not talk about this geometrical interpretation that we have developed, does not talk about anything about the differentiability of the curve. For example, what I can do here is I can draw a straight line. Again, it's not very straight, but let's try it again to draw a decent enough straight line. And you see, I can have the curve like this way. You see, it is still the chord. I can choose x1 and x2 like this way, and essentially what I will have is I will have this inequality satisfied for this particular function, but yet the problem with differentiability will come at this point. So here is what I want to do. I want to see if I can modify this to take into account the differentiability of the curve. Now for that purpose, let us write down x1 as x0 and x2 as x0 plus delta x. If this is the case, then f of lambda x1 plus 1 minus lambda x2 is equal to f of lambda x0 plus 1 minus lambda x0 plus delta x. One can expand this now, right? So if you expand this, this becomes lambda x0 plus delta x minus lambda x0 minus lambda delta x. This gets cancelled out. So essentially you will have x naught plus delta x. So you have x naught plus essentially you have x naught plus delta x minus lambda delta x, which you will simply recast as f of x naught plus 1 minus lambda delta x. The right hand side, the inequality now takes the form f of x naught plus 1 minus lambda delta x is greater than equal to lambda f of x naught plus 1 minus lambda f of x naught plus delta x. Good. Let's see. So I have a 1 minus lambda in the right hand side. So let us write down this as 1 minus lambda fx naught, put a minus sign in front, plus 1 minus lambda f of x naught plus delta x. And since I have put a minus, I have added a minus fx naught, I need to add an fx naught over here to keep the right hand side as same as the above one. And here of course I have fx naught plus 1 minus lambda delta x. Let's bring this part to the right hand side, which would mean that f of x naught plus 1 minus lambda delta x minus f of x naught is greater than equal to f of x naught plus delta x minus f of x naught. There is a 1 minus lambda which is there and which I am going to bring over here, right? Not very complicated. It's very simple algebra that we are doing over here. Now let's take the limit of lambda to 1. If I take the limit of lambda to 1, essentially the left hand side I have is f dash x naught delta x must be greater than f of x naught plus delta x minus f of x naught. I'm going to recast this equation again and I'm going to write f of x naught plus delta x must be greater than f of x naught plus f dash x naught delta x. And this is the equation that we have come down to. If you look at this equation very carefully, then you will realize that the right hand side, the one that we have over here, is the equation of the tangent at x equal to x naught, right? This is simply the value of the function at x naught plus delta x. And therefore this inequality means that the tangent is above the curve. Sorry, there has been a slight error with the sign change. This, if I just follow it from over here, I am bringing this term to the right hand side, therefore this must be less than equal to, and therefore this equation essentially tells you that the tangent is always above the curve. So what we started off with is essentially we started off with the fact that the chord is below the curve, and one can bring x2 closer to x1 and x1 so that you will see that the tangent comes up above the curve. Now if this is the case, if the second derivative exists, so here of course when I have written down this particular term in the left hand side, I have assumed that the first derivative, the assumption here first derivative exists. Further, if I now assume that the second derivative exists, then essentially I will expand the left hand side to write down as delta x f dash x naught plus delta x whole square over 2 f double dash x naught must be less than equal to f x naught plus f dash x naught delta x, right? One can of course say, why am I not considering the third derivative? Well, because essentially you have done extreme calculus and therefore you know the principle of extrema, how to determine extrema, and it's a sign of the second derivative which determines everything. Therefore it suffices to keep the second derivative. It's essentially the rate at which the tangent is turning, and you immediately see that f double dash x naught is less than equal to 0, and this would imply that this is a stable equilibrium. But we had started off with a function of a single variable. If I now want to generalize to a function of more than one variable, then this would mean that this equation translates to d2f is less than equal to 0. I invite you to work out this relation. Hence, for the entropy, a maximization means that d2s is less than equal to 0. What about the internal energy? Well, for internal energy, I know the system goes to a stable equilibrium minimization of u, and therefore one can immediately see that if the same line of argument that x1 plus x2, the composite system, the internal energy of the composite system must be less than u of x1 plus u of x2, right? And now therefore one writes down x1 as, let's say, lambda times xi1 and x2 as lambda times 1 minus lambda times xi2, and therefore use the homogeneity principle of the internal energy as we have used it for the case of the entropy. It follows lambda xi1 plus 1 minus lambda xi2 is less than equal to lambda u of xi1 plus 1 minus lambda u of xi2, which of course means that again if we consider a function of one variable, that translates to lambda x1 plus 1 minus lambda x2 is less than equal to lambda of f of x1 plus 1 minus lambda f of x2, right? Now we are tempted to draw the function. So we look at x1, we look at x2. Clearly, let's say the function has some value f of x1, and at this point it has some value f of x2. And this essentially means the value, so x1 plus x2, if you take any midpoint over here, any intermediate point between x1 and x2, which is represented by lambda x1 plus 1 minus lambda x2, and the function value of this must be less than the chord. So essentially you have a function which is something like this, right? Such functions are called convex functions, right? Now, what does, again, this definition, the way we have written it down, it does not take into account the differentiability of the curve. And if we have to look at the differentiability of the curve, we have to do the same thing that we have done over here. We have to follow the same route that we have done, and you will see that this would come out to be d2u is greater than equal to 0. Therefore, as far as thermodynamics is concerned, as a system goes to an equilibrium, it maximizes the entropy, which would mean that d2s is less than equal to 0, or it minimizes the entropy, which would mean that d2u is greater than equal to 0. Similarly, for the other thermodynamic function, one can show that for the Helmholtz free energy, d2f is less than 0, f is a function of tv and n, d2h is greater than 0, d2g is again greater than 0, and d2 omega is again greater than 0. H is a function of Spn, if you recall your Lagrange transformations. Sorry, legendary transformation, not Lagrange transformation. If you recall your legendary transformation, G is a function of T, P, and N, and omega is a function of T, V, and mu. So this forms the stability criteria for a thermodynamic system.